Welcome back, and thank you very much for watching this lecture video. And I'm here with another lecture from organic chemistry. In the last couple of lectures, I talked about aromaticity. And we said we can have aromatic or non-aromatic compound. And aromatic compound, we said we need to be flat, cyclic, and we need to have a p either empty or fully occupied p orbital on each atom, and at the end, number of electrons supposed to follow 4n plus 2. Okay. Aromatic compounds are stable way more than what we expect them. Okay, so they are stable more than what we expect them. Non-aromatic compound, and when we calculate the stabilization, it happen to be exactly as we expect. Okay, so nothing is surprising when it comes to non-aromatic compound. Aromatic, more stable than we expect. Non-aromatic, as stable as expected. Okay, but how about anti-aromatic? And what's an anti-aromatic? Anti-aromatic, they are less stable than whatever we expect it to be. Okay, so they are less stable, something making them less happy. And we're going to go after this one. And what's the factor here? What is it? What's the like the effect or whatever that is make them that unstable? Okay. How do we get anti-aromaticity? And we're going to follow again the Huckel rules and with some modification. And first, the molecule is supposed to be planar, and then cyclic. On each atom, we need to have fully occupied or an empty p orbital. And next number of electrons will follow 4n, not 4n plus 2, just 4n in order to get a conjugated pi system. Now, the third one, okay, later you might see that, oh, there is a contradiction here. For the third one, simply translated this. On each atom, we're supposed to have a p orbital, okay? On each atom, we're supposed to have a p orbital. And that p orbital is supposed to have either, supposed to be empty, okay? So empty, or put 2 electrons in it. Okay, so this one, it will be full. Okay, and these two, they were empty. So either empty or fully occupied, and just have a p orbital on each atom. Okay, so let's follow this cation. This cation is planar. How do I know planar? Because each carbon, it has sp2 hybridization, including the carbon with a positive charge. And sp2 hybridization will give us a trigonal planar geometry. So the molecule is a planar. Next, is it a ring? Yes, it's cyclic. And do we have a p orbital on each atom? Yes, we do. We have 5 of them. And so on 4 of them, we have electron, and 1 of them, it will be empty. So totally, we have 4 electrons. So I'm going to say I have 4 electrons, or we have 2 pi bond. That means we have 4 electrons. So this one, it will be following 4n. And what's the n? N is going to be 4 divided by 4. It will be 1. So this system, we say, is anti-aromatic. Okay, anti-aromatic compound. Okay, let's go through this examples and try to figure which one is aromatic or anti-aromatic. So pause the video here and try to practice all of them one by one. Okay, great job. And so the first one, I see 1, 2, 3 pi bonds. 3 pi bonds means 6 electron. System is cyclic. All atom will have sp2 hybridization, including oxygen. Remember, oxygen does have a lone pair, the second lone pair. And where is the second lone pair? This is going to be the second lone pair. It will be pointing out of the ring. So we are not going to include that lone pair and the second lone pair of oxygen. The first one got involved to make a double bond with carbon. Okay, so I have 3 pairs, means 6 electrons. So I'm following 4n plus 2. And that's going to be equal to 6. What's going to be the n? And it will be 6 minus 2 divided by 4. That's going to be 1. So n is going to be equal to 1. And this molecule, it will be an aromatic. So, okay, this, I'm going to say it will be aromatic. Okay, next one. The next one we have 1, 2 pi and 1 lone pair. Okay, 1 lone pair. So we have 2 pi, 1 lone pair. That means we have 3 pairs equal to 6 electrons. So this system, it will be aromatic. Okay, aromatic compound. And next one, look to this carbon. That carbon, it has sp3 hybridization. We don't have an empty p orbital there. Now, number of pi bonds, 1, 2. So we have 2 pi bonds, means 4 electrons. So this system, it will be non. Okay, this system, it will be technically, let's see, we have sp3 there. sp3 because it doesn't have an empty orbital. It doesn't have an empty p orbital, so I'm going to call it non. Okay, non-aromatic. Not anti. Be careful. Okay, this is non-aromatic, not anti. Okay, and because one of the carbon atom, it has sp3 hybridizations, that means the molecule is not non-flat. Okay, or not planar. And because it's not a planar, it will be non-aromatic. Okay, how about D? D, we have 2 pi bonds and an empty orbital here. So this one is empty. Okay, do I have a pi bond? Sorry, do I have a p orbital? A p orbital on each carbon atom? Yes, we have a p orbital on each of them. So do we have a conjugated system? Yes. How many electrons do we have? We have 4 electrons. So this system is following 4n, and n is going to be equal to 1. So this system, I'm going to call it anti. So D, it will be anti-aromatic. Okay. How about E? E, we have 2 pi bonds, means 4 electron. Okay. How about the hybridization? Is the molecule planar? Yes, the molecule is planar because the hybridization of each carbon is going to be sp2. So all carbon atoms coming with sp2 hybridization. So the molecules will be a planar. And do we have a p orbital on each atom? Yes, it's cyclic, it's flat, and we have sp2 hybridization, number of electrons equal to 4. So we are following 4n, and we have 4 electrons. In this case, n is going to be equal to 1. So this molecule also will be anti-aromatic. So I got 2 molecules, aromatic. A and B are aromatic. C is non-aromatic, and D and E are anti-aromatic compounds. Anti-aromatics are less stable than non-aromatic. The most stable one, it will be aromatic, then non-aromatic, and then anti-aromatic. Okay. Now let's talk about the fact why anti-aromatic compounds are such an unstable compound, and what's the difference between anti-aromatics and non-aromatics, why they are less stable even than non-aromatic compounds. So in this case, we have a molecular diagram of benzene molecule. The benzene molecule, it has 3 pi bonds. Okay, if you just look to the pi bonds and try to draw the molecular diagram of the pi bonds, they will show up on the top of the molecular diagram. You will have the first pi bond with 2 electrons, and as you see here, we don't have we don't have technically a node, and on the top, forgive me, on the top we have okay, we have all the orbitals are with a positive sign. Okay, so we have a conjugated system. We have a p orbital and on each carbon atom. And next one, okay, we have 2 orbitals, pi 2 and pi 3. And those orbitals, again, they are occupied, but each one, it has a node. How do I know how many nodes I have? Okay, go with this. Go with n minus 1. Okay, the first level, if n is equal to 1, n minus 1, 1 minus 1, it will be 0. So there will be no node. And the second one, and n in this case is going to be 2. So you will say 2 minus 1, we will have 1 node. Now, where can I put the node? Node, I can put it here. I can put the node there. Okay. And if I put the node between, like a crossing, actually 2 bonds, and like this one, on one side of the molecule, I have 3 p orbitals. Okay, 3 p orbitals with the same phase. They will be positive, so that we will have a conjugated system here. And if I go with, like on the left side, they turn to red, and they will have a negative phase. And those, they will have, like, and again, conjugated system. And when the conjugated system, we get it through 3 p orbitals. Okay, we do have a node. Okay, and 1 node. Now I can put the node this time crossing 2 carbon atoms, and if node pass 2 atoms like this too, and because we can't have a chance of finding an electron wherever we have a node, on these 2 carbons, the one I'm going to highlight, this carbon and that carbon, we're not going to have a chance to find electron there. That means we're not going to draw any orbital there. And as you see, I did not draw any orbital there. Okay, so now I have 2 atoms up. They can actually do interaction, and we will have a positive interaction between them, or 2 red orbital on opposite phase, and they will give us technically this section. Okay, so I have 3 pi bonds, and we got I showed you the molecular diagram for them. The highest pi occupied orbital, we call them HOMO. Highest occupied molecular orbital. So HOMO stands for the highest occupied molecular orbitals. Okay, and those orbitals are fully occupied. Now look to the LOMO. Okay, what's a LOMO? Lowest unoccupied molecular orbital. The LOMO has 2 nodes, 1, 2. Okay, 1, 2. And LOMO, this time, they are empty. We don't have any electrons inside them. So when I look to my HOMO orbitals, they are fully occupied. Because they are fully occupied, the system will be happy. System is stable, and it will not go after chemical reaction. Why? Because the orbital is already full. Why do you want to put electron inside of it? And that's the reason benzene will not get involved in, for example, addition reaction easily. If you add HBr to benzene, this reaction is not going to happen easily because the orbital is already fully occupied, unless you are using anti-bonding orbitals. In that case, again, system will try to resist, and unless you force it, in that case, you will get rid of the aromaticity. Okay, so this is the reason benzene is not that reactive compound, because it's aromatic. Now, let's look to cyclobutadiene. Cyclobutadiene, it has 2 pi bonds. Okay, the first pi bond, it doesn't have any node, and is 1. Okay, so n minus 1, I go 1 minus 1, no node, 0. In this case, n is going to be 2, n minus 1, I go 2 minus 1, I have 1 node. Where can I put the node? I can put the node here between crossing 2 bonds, or, okay, and then in this case, perpendicular to the first one. Okay, so I get 2 pi bonds, okay, 2 pi bonds that they have same energy. Okay, now I have 4 electrons. Out of 4 electrons, 2 of them, I put them inside pi 1, and I'm left with 2 more. Where can I put those 2 electrons? 1, I put it here, and the second electron is there. So now I got 2 pi bonds that they are singly occupied. So now I have some orbitals that they are not fully occupied. And because they are not fully occupied, they will be looking for electron. And this is the reason that the cyclobutadiene is not stable, okay? Because the orbitals are not fully occupied. They are not either empty or fully occupied. And if you have some unoccupied, or you have singly occupied orbital, the system will be reactive. The reason that this molecule, we call it anti-aromatic, because it has HOMO, okay? highest occupied orbital with some electrons, okay? Some electrons. The electrons are not fully occupying the orbitals. They are half occupied. And because they are half occupied, this system, it will be anti-bonding. In quantum mechanics, we say we have a triplet state, okay? We have triplet state. We have two electrons that they're pointing up and two different orbitals. This system, this one, it will be very reactive based on quantum mechanics. And if you want to translate in organic chemistry, if you have an orbital with singly occupied with just one electron, that system, it will be reactive anytime you get just one electron in any orbital. Okay, and I have a model here that we call it actually a Frost circle, that you can use it to predict whether in one system it will be aromatic or anti-aromatic. And I'm going to practice this one in next lecture video. For now, thank you very much.